Good morning again, everyone. This is going to be our last lecture in chapter 16. We'll be able to finish it today and get through the rest of the information in this chapter. So we have been talking about spontaneous reactions, and now we're going to talk about free energy. It's a thermodynamic function related with spontaneity, and useful in temperature dependence of spontaneity is called Gibbs free energy. So Gibbs free energy was studied by Josiah Willard Gibbs in 1839. He was a Yale professor in physics that was studying a way to study spontaneity with temperature and pressure. So if we have a process at constant temperature, he found and developed this little equation here. So our change in G, which is our change in Gibbs free energy, is equal to our change in enthalpy, subtracting the temperature times the change in entropy. Now, if we take a look at this right here, remember we got to keep the same thing as chemists, that there isn't a subscript here, so you might be thinking, is it the universe, is it the surroundings, is it the system? When there is no subscript in anything that we are doing, we are always referring to the system. So it's going to be the change in heat of the system minus the temperature times the change in entropy of the system. So it's a way to determine, is this going to happen spontaneously? This means that a process carried out at constant temperature and pressure will be spontaneous only if delta G is negative. Now, this is not a rate dependent, and we haven't really talked about rates too much yet, so we will just say that this is going to be negative. And you can see that if we know that this has to be a positive value in order for entropy to increase, this is an exothermic reaction, that is going to be negative. So overall, delta G does need to be negative in order for it to be spontaneous. So Gibbs free energy is not something that's measured. We're just taking the different situations and applying them in this formula. So a negative Gibbs free energy, the chemical reaction will move from left to right. That's just our normal way that we read our chemical reactions. Again, if delta G is 0, if we are at equilibrium, just as we saw with our change in entropy. And if I have a positive Gibbs free energy, it will be spontaneous from right to left. So this again is in our reverse situation that we just talked about with entropy. So if we talk about our change in entropy of the universe, again, the only way it's going to be spontaneous is if this is going to be negative. So in order to have a spontaneous reaction, I feel like I'm saying it a lot again, we have a negative Gibbs free energy and a positive entropy in our universe. And so it's just another way that we can predict spontaneity. That's all we're trying to do here. We're predicting spontaneity by saying that yes, if I have positive entropy, the reaction is going to happen. If I have negative value for Gibbs free energy, I'm also going to have a spontaneous reaction. So again, we are still talking about heat flow. We are still talking about positional probability. Remember gases, we have a ton of positional probability. And we also talk about our heat flow. So these are all review things in this chapter. We are not doing all of this chapter 16 because it starts getting into some more calculus that many of you have not had. So we had our first law of thermodynamics about energy remaining constant, second law of thermodynamics where entropy is always increasing, and now we have our third law of thermodynamics that says the standard state of entropy of a perfect crystal at 0 Kelvin is 0. Now, this is only an ideal observation. Remember, if Kelvin is 0, we are at absolute 0, 0 Kelvin. So we are at absolute 0. We know that that's not attainable, so this is just an observed behavior. Remember, the standard state is always 25 degrees room temperature and standard pressure at 1 atmosphere. Now, we've already done this in the last chapter. We did product minus reactant. You have your change in heat of formations. You have similar charts for entropy and Gibbs free energy. You can do the same thing in all three of these cases, which we'll work through a few of these problems in class, that you have all these charts and you can take product minus reactant, and then depending upon the sign that you get, whether it is spontaneous or not. And remember, for this, we know that it's going to be spontaneous if that is negative, if this entropy is positive, and Gibbs free energy is negative. So if you can't analyze the equation to figure these things out, you can do it by values. So we're going to be making some predictions, and then you can actually calculate them. So this is a lot of repetitive stuff in this chapter. You can see standard free energy change in Gibbs energy, the standard state, will occur if the reactants in their standard state are converted to products in their standard state. So these are the methods that we can use to determine them. Here's our formula that we just looked at, and we will work through some of the examples in class. Application of Hess's law, which all of you love and find very easy to do. Product minus reactant if you're given charts of Gibbs free energy. And again, this is the change in Gibbs free energy in its standard state. That's how you say that. The change in Gibbs free energy at standard state is a formation of element in its standard state, meaning that, you know, oxygen is diatomic as O2, or plain old aluminum, or plain old copper, and we can take a look at all of those values. And just like you saw before in your change of standard state of change of enthalpy, these are also going to be 0. So we cannot directly measure this. Remember, we are just talking about trying to determine if a reaction is going to happen spontaneously or not. I think that's it. So we are done with chapter 16. We are going to be testing on chapter 6 and 16 together. It's mainly going to be multiple choice. So I would encourage you to re-listen to these podcasts, or else do some reading in your book, and that will also help you sort out some of this information. Have a wonderful day.